In this lesson, we're going to learn about right triangles and creating similar right triangles out of them. It turns out that if you start with a right triangle, like this one, ABC, and you draw an altitude that starts at the right triangle and comes down and hits the hypotenuse, that this altitude divides this triangle into two smaller ones, the red one and the blue one here. And these two smaller triangles are similar to the original triangle, meaning that their side lengths are proportional. We can show they're similar. It's not too bad. To show they're similar, we just need to find, we could use the theorem angle-angle similarity, meaning if we could find two pairs of angles between each of these triangles that are the same size, then we know that the side lengths are proportional and all the rest of the angles are the same length, same size. It turns out there's one very obvious one, the right angles, because this starts as a right triangle and in altitudes create right angles. We have one pair of angles already built in. And if we look at the original triangle, how these were made, if you look at the red triangle, this angle A, well, it's the same as this one because I just cut the triangle in half. So these two have to be the same angle. And now the big triangle and the red triangle share two angles that are the same size. On a very similar note, the blue triangle and the original triangle have to be similar because they each have a right angle. And now this time this blue angle, or this angle B, hasn't been changed at all. It's the same as in the original big triangle. So this blue triangle is similar to the original black one. And it turns out that because the angles of a triangle always add to 180, that this third angle, this angle C, has to be the same size as the third angle in the big triangle, which is the same as angle B. And similarly, this smaller angle that's kind of a part of the original right angle in the blue triangle is the same as the original angle A. This is really useful because what we know is that these two smaller triangles, now their side lengths that correspond to the original triangle are all in the same proportion to the big triangle, meaning we should be able to set up and solve proportions to find some missing side lengths. We're going to start though by just visually identifying what the corresponding parts are and writing down what the similar triangles have to be. I like to do this by drawing three copies of a triangle. They can be larger, smaller size, but I'm going to draw each of these, the big triangle and then each of the two smaller parts out. I'm going to label them for their corresponding parts. And moreover, I'm going to draw them so they're all in the same orientation, meaning that all the corresponding parts are in the same spots. And I like to do that based on what the original triangle looks like. So I'm going to draw just a copy of my original triangle here. And again, this drawing does not need to be perfect. In fact, mine's pretty bad, but it's okay. This real triangle has vertices of M, Q, and P. And then now I have two smaller triangles. And again, these are just rough sketches because my drawing ability is pretty bad, especially on a computer. But they'll get the job done. I'm going to outline this first one in red. Kind of better see. We'll say this first triangle down here is M and Q, and I want to put the corresponding parts in the same places. Well, I know that the right angle is going to be on top, and the right angle of the red triangle is at point N. So I know there's going to be an N up here. I also know that angle M is in this red triangle. It hasn't moved. Angle M is should still be in the bottom left-hand corner. So this should also be an M. So the only letter left over, the only vertice that hasn't been used yet, is Q. So that forces Q to be down here. Play the same game with the other triangle. And what I see is that in the same fashion, N is still the right angle, so N has got to be up here. This time the one angle that hasn't moved is P, and therefore the only thing left is a Q. So redrawing these triangles, I know that now I can visually see what are all the sides that are in the same proportion. And then if I was tasked with solving a problem, I could then now very clearly write out what sides are proportional, what sides. Further, we can write out what triangles are similar to each other as a similarity statement, which is something you would be tasked with doing. Triangle MQP, MQP, that should be similar to triangle in the same order MNQ. And they're also similar to triangle QNP. We can use this now. If we can draw triangles, this is a general strategy that'll work for solving any similar right triangle problem. And you can always draw out 3 triangles. You can always, in a second, we'll see how to label them. And then we can use the labeled triangles to write and solve some proportions to find missing values. I'm going to start this problem to try to find this value of x in the same way we started here, by drawing out 3 triangles. I'm going to draw them in the same orientation as the original triangle. They're all, the original triangle is the right triangle down here in the bottom left hand corner, so I'm going to draw it there. This first one will just be the original triangle, GEF. How about we make this second triangle, we'll do it in red, just for more visual sake. It looks like its right angle is H. The red angle E is exactly the same as the original angle E, so this should be an E. And then the only point left is angle G. And in the same fashion, how about call this one a blue one? Again, H is the blue right angle. This time F is the angle that hasn't moved. It's in the same orientation, so F should be in the same spot here. And then therefore G. It's got to be up front. With this, I'm going to now take the lengths, the labels from the original triangle, and everywhere I see those lengths in the smaller triangles, I'm going to fill them in. So for example, everywhere I see an EF, I'm going to write a 5. So EF is 5, and I don't see any other EFs. Everywhere I see an EG, I'm going to put a 3. So 3, and I also see an EG over here. Everywhere I see a GH, I'm going to put an X. See, no GHs up here. There's a GH down here. That's X. There's a GH over here. X. And everywhere I see a GF, I'm going to put a 4. So 4. No GF here. Oh, here's a GF here. 4. With this drawing, should be able to write and solve a proportion to find this missing variable x. I see 2 ways I could do that. Between the first and the second triangle, I see that the hypotenuse compared to the hypotenuse, so 5 compared to 3, is the same as the bottom leg compared to the bottom leg. So say 5 to 3 should be equal to 4 to x. Alternatively, maybe I saw that I could use the first and the last triangle, because hypotenuse compared to hypotenuse, 5 to 4, should be the same as the vertical leg compared to the vertical leg, or 3 compared to x. Since it's all the same triangles, no matter how I set up the proportion, when I'm done cross multiplying, I should end up getting the same answer. So with that in mind, I'm going to use the first 2 triangles here. I'm going to say 5 compared to 3 should be the same as 4 compared to x. When I cross multiply, I get 5 times x is equal to 4 times 3, or 5x equals 12. Therefore, x is equal to 12 over 5. If you want, you could write this as a decimal. As a decimal, this is 2.4. But I think as a fraction is the best answer.